Right. So next we will look at another kind of register, which is a variation of the register, what we call a shift register, or parallel load and shift register, where we can load the data into the register, and also we can shift the data from the left to right in this case. So the operation is either shift or load is depend on this signal, what we call the shift load signal. So if we look at the circuit here, uh, when this signal equal to 0 or the shift is active, so means that the input to this flip-flop is from this. So it will go to this. And also for the second flip-flops, instead of from the parallel data here, but it is from the first flip-flop here, go to the second flip-flop here. And also the same as this one, the third flip-flop, where the input to the third flip-flop is coming from the second flip-flop here, because this one is 0, see, 0. And again, the uh, input to this flip-flop is from the output of this flip-flop. Means that we shift the data from here to here, from here to here, from here to here, and from here to here. So the shift operation will looks like this. Yeah. For example, this is our uh, register, and this is a 4-bit register where I draw like this, and we have this is a register where this is bit number 0, this is bit number 1, this is bit number 2, this is bit number 3, and the data is coming from the outside here. And for example, the data is initially we have 0, 1, 0, 0. So when we do the shift operation, what happens is that the next clock cycle, our data will be like this. Okay, for example, the data here come from the outside is 1. So we will have 1 here, and this bit will go to the next flip-flops, and this data will go to the next flip-flop, which is number 0, and this will go to the next one, which is 1 here, this 0, and this 0 will go out from the register. So this we call shift operation, right? So we can use the register to shift the data as well. And shifting is very important in digital system. We will see in the next chapter, chapter 5 and chapter 6, how we use the shift in the system. Right. So the shift in the register is like this, and when the signal here is 1, what happened is that the data is not shifted, but it is it will be loaded with a value from this input, right? And it is loaded. It will be loaded uh, parallelly or at the same time, because look at this. When this signal is 1, 1, 1, 1 here, so this will go to this, and this also will go to this, and this will go to this, and this will go to this at the same time. So that will we call parallel input or parallel load. Yeah, and of course the output here is parallel output. So again, this is called the parallel shift. register, parallel load or parallel access shift register. How to create this parallel shift load register? So we have many ways to create this circuit. One way is to use the hierarchical design methodology, where we create one parts here or one bit here, the flip-flop with the multiplexer here, and then we instantiate, call or import this into a new design where we connect like this. So we can create the one part here, this, all right, using this. Okay, so if the flip-flops here, we create this part. So look at this. If select this one, right? In this case, we name it as select equal to 0. So D0 will go to Q. Else, if select equal to 1, D1. So what we will have is something like this. We will have the flip-flops with the multiplexer here, and we will have D0 and D1 and 0, 1, and this is D, and we have post H clock, meaning that this clock is positive H, and of course we have Q here. So and we have a signal here called SEL, and when this SEL equal to 0, we have Q equal to D0, and when this SEL equal to 1, we have Q equal to D1. Right, straightforward. Or we can use this style of coding or modeling. So we can create the multiplexer first before the flip-flops. So this also will give you the same circuit like this. Here is this multiplexer. All right, D. Of course, you will have D signal here. D. You name this as wire D. And if select equal to 1, D1 will, or D will equal to D1, and if select equal to 0, we have D equal to D0. So you get this flip-flop, and this will create this, this will create this multiplexer, and this will create these flip-flops. Q at post H clock. So Q is equal to D. So you will have the same circuit using different style of code. Next, you can connect this together to create this circuit, right? So in this case, you will have mark DFF, which is this one, or maybe this one, either one. Stage number 3, W. In this case, W is this. This is W. So let's name this as W. This is W. And R3 is this D0. This is W. This is R3. So meaning that this is R3, this is W, and L is this SEL, L. So this is L. And you have clock, yes, because you have clock here, and you have Q here. Q in this case is Q3, yeah, for this one. Done. And for the second stage, we call it stage 2. So Q3, is it the input for this one is Q3? Yes, Q3 here. And this one is R2, and of course connect to the same L, and you have clock, and the output is Q2. The output is Q2. And then this is the third one, and this is the last one. And you can have this circuit. Or you can code this way, all right, where you're not using this as a submodule. This one, you create a new one where you can write like this using behavioral code. If L or if load, so Q equal to R, all right, you load R into Q. When L or load equal to 1, all right, when equal to 1, you load R into the register. But if L equal to 0, means that we want to do the shift. So to do the shift, we can do this, where W is assigned to Q3, Q3 assigned to Q2, Q2 assigned to Q1, and Q1 assigned to Q0. So this is the same things. W is assigned to this Q3, Q3 assigned to Q2, Q2 assigned to Q1, and Q1 assigned to Q0. And you will have the shift load register as well, right? Or you can have something like this, where you use the for loop statement. And this for loop statement is good because it is flexible, where we can change the size of the register. In this case, is 16-bit register, so we have 16, and everything here is 16. So this will create the same circuit as this one. You just unroll the loop, and we will have the same circuit, right? So you can try to do that. Now come to this. This is the same actually, the one that we have learned, which is the same as this one, the register with the load signal or enable signal. So same thing actually. So this is the code. So it's the same actually, but this one using parameter where you can change the size anytime as you want. So this is alternative code, yeah, where you can have also for this one. Now we have the counter, right? How to design the counter using the register. So for example, we want to design a counter like this, yeah, where we have a register here, a 4-bit, and we have the adder here, and we write the code like this. So for example, we have always block next edge reset, because this one is active high reset. So we write next edge reset, and the clock is positive edge clock. So we have positive edge clock. So if reset equal to 0, this is how we write. If reset equal to 0, the output of the counter is equal to 0. But if enable equal to 1, or if not reset, means that reset equal to 1 in this case. Yeah, if reset equal to 1, so we will look at this E signal. So if E equal to 1 in this case, the output C is equal to C. This is C plus 1, right? This is C plus 1. So this is an adder. This is an adder plus 1. So we have the up counter. So this counter will count 1 in step 1. Yeah, C is C plus 1, means that the output here, if we start from 0, it will be 0, 1, 2, 3, 4, and so on. But if we want to have the two-step counter, we can have +2 here. So we can start from 0, 2, 4, and so on, right? So in the Verilog code, it is very easy. And this is another example where we have two multiplexer here. In this case, if reset, of course, C equal to 0. If L equal to 1, of course, this output is equal to R, means that we can load any value into the register. And when E equal to 1 means we count. Yeah, when E equal to 1 means the input to the register is the input from here, which is the counting, right? Means that this counter can count from any number. We can load any number into the register and start count from there. Whereas for this one, this will always count from 0, because when we start reset, we cannot load any value into the register. So we need to count from 0. But this one, we can load any value into the register by set this L equal to 1 and get the input from this art input. So for example, you load 2, art is equal to 2, and L equal to 1. So these 2 will go to the register, and we start from 2, and then we disable this where L equal to 0, and it will start count 2, 3, or you can have start from 5, for example, R equal to 5. So 5, 6, 7, 8, 9, 10, and so on, right? So this is very useful design where we can start count from any number. And this is another counter, a variation of counter where this one will count until a certain number and give signal, tell you that the number that we want to detect is detected. So for example, if all we want to know whether the counter is full or not, all right, means that count to the full capacity of this counter already. Means if we have 4-bit counter like this, the output, the maximum output value will be 1, 1, 1, 1. So if it is full already, so this signal will be activated because this is AND gate. If C3 equal to 1, C2 equal to 1, C1 equal to 1, C0 equal to 1, then this signal should be equal to 1, right? So this is very useful also in when we design a circuit later on. When we have the counter and we want to know if the counter is full or what we call overflow already, so we can get this signal, because the counter is used to count a number. So we can actually design a circuit to count to a certain number, and we want to know whether it is counting to that number already or not. If it is the number that we want is detected, then we can know using this signal. In this case, it detects the full value of the counter, which is 1, 1, 1, 1. So you can change this to any gate combination to detect other value. All right, and I think this is the last one for today, which is the memory circuit. The memory is very important also in digital system, where we use the memory to store data, to store a lot of data. Before this, we learned register. We use register to store data. For example, an 8-bit data, we use one register to store. When you have another 8-bit data, you need another register to store. But what if you have 100 of data, right? So you need 100 of register. So that is not the best way to keep or to store the data. So uh, a, a better way is to use what we call a memory, all right? Just like your computer RAM, computer memory. So this is how we create the memory in Verilog. But before we create the memory in Verilog, let's see how the memory work, or how the memory looks like in the system. So this is an example of the memory, how we draw the memory in the design. And this memory is a 1K memory, 1 kilobyte memory, because one memory location, we call memory location, is 8-bit here, or 1 byte. Yeah, 0 to 7 is 8-bit, and 8-bit is 1 byte. So one memory location here is 1 byte. So we have 1024, including 0. So because this is 0, 1, 2, 3, so the last number will be 1, 2, 3, 4. But in total, we have 1024. So 1024 in digital or in computer is 1 kilo. In this case, this is 1 kilobyte memory, right? And this is called address. Yeah, this is called a memory address. And we can see that each memory location has a unique address. For example, this one, the address is 0. This one, the address is 1. This one, the address is 2, and so on until we have the last address is 1023. So normally the address will be represented in a binary number or hexadecimal number. So 1023 in hexadecimal is actually 3FF. So we can have here 1023 in hexadecimal is 3FF, right? Now how we create a memory in Verilog? So it is actually very easy, and it is declared as something like this. To declare a memory like this, in Verilog is declared as rec 70, the name of the memory. So the name in this case is MEM. So you can have any name that you want. All right. In this case, we name is MEM. So this is the size of each location, which is 8-bit. And this is the size of your memory, how many locations that you have. So in this case, you start with from address 0 and end with address 1023, right? This is the last address, and the size of this memory is 1 kilobyte, right? So how to write now? The question is how to write into the memory, right? So the syntax that we use is this. For example, our data is in this case is 8-bit, right? We want to write into memory location 21, somewhere here 21. So this is how mem square bracket the address of the location that we want to access equal to the data that we want to put in. And to read from the memory, again, this is the data, the variable, and this variable is 8-bit. And for example, we want to read from memory location 250. So this is how memory 2250, and we get the data from here. And we also can initialize the content of the memory. So for example, we want to initialize the content of memory location 100. This is to initialize the bit, bit, because we have 8-bit, right? So for example, at memory location 100, bit number 0 of 100. So this is how 100, bit number 0, we set 0. This will initialize bit 0 of memory location 100 to 0. Okay, when you put 1 means that you set memory location 100, 100, bit number 1 to 1, bit number 0 to 1, sorry. And this is the Verilog code to create a 1 kilobyte RAM or memory in the Verilog. And this example use what we call the synchronous write and asynchronous read. What is that? Synchronous write means that when we want to write, we need to have enable signal, right? Just like this register. This is actually synchronous write, where you need to active the load signal in order to write any data into the register. But to read the content of the register, you can read anytime. So read anytime means that asynchronous read, because it is connected to the output of the register. So the value here is always available, right? That is meant by synchronous read or asynchronous read. All right. So in this case, this is the memory that we want to create, and the address must be 10 bit. Why 10 bit? This is because to represent this value 1023, you need 10 bit size. Yeah, again, because this is our memory, and the address starting from address 0, and the last one is 1023, and in hexadecimal this is 0, and this is 3FF. And of course, if you have 3-digit hexa here, you need 3-digit hexa also here. And if you change this to binary, it is actually 1 1. Yeah, 3 is 1 1, F is 1 1 1 1, another F is 1 1 1 1. See, all these are 10 bit. All right. So in order to represent this number, you need at least 10 bit. That is why here we need to have 10 bit address. And data, of course, 8 bit. And we have data out. This is data in, 8 bit. Data out, also 8 bit. And we have one signal, we call it synchronous write, or we call it WE in this case, or synchronous write. And of course, we have the clock signal here. Now, how to create this in Verilog? Very easy, actually, based on this. So in for declaration, of course, the address is 10 bit, so 920, 10 bit. Data in is input 8 bit, 720. These two signal are 1 bit, clock WE 1 bit, data out 8 bit, 720, and this is declaration of the memory. 720, the size of each location is 8 bit, and the name of our memory MEM 0 to 1023 means that we start with 0 and with 1023, right? We have 1K location, unique location. And to create the circuit, this is how. Data out here is equal to MEM square bracket address. So this address can be any number, right? From 0 to 123, 1023, right? So this is data out. And here we use always post H clock. So this is post H. If WE equal to 0, In this case, should be equal to 1. Change this to 1. Okay, because we have the positive active high WE signal. So if WE equal to 1, then we write into the memory. How to write into the memory? Data in is assigned to memory, but which address? So depend on what is the value of the address. That is how, very simple. Then you will get the 1 kilobyte RAM. When you want to change the size of the RAM, so just change this value. You will have different value now, right? So that will end the lecture today. Yeah, we have learned a lot. We have learned the latch, uh, uh, the basic memory circuit, which will be used to create the sequential circuit, and we have learned the D flip-flop, which is a very important circuit to create the register that we use to store the information or data in the ether system. And also we learn the application of the register where we can shift the data, and we also learn another application of register where we can create the counter. So the counter, we can create actually the up counter and down counter. To create the down counter, you just change the adder into a subtractor, then you can get the down counter. And to store or to save many data, you need to use a memory. And now we learn how to create the memory in Verilog. So these all are very useful, and we will use this a lot later on in design a more complicated circuit. And of course, the actual circuit that we can use in designing or for solving engineering problem. Okay, so that will be the lecture today. Thank you very much.